today's lesson. Today we're going to look at reflections, and we're going to see how functions behave when we reflect them across the y-axis, the x-axis, and a few other little things. So let's start off with what's probably the easiest reflection, reflecting across the x-axis. So, how do we accomplish this? Well, if we have a function and we want to reflect it across the x-axis, then it's a very simple thing to do. The only change we have to do is put a negative in front of the entire function. And that has the effect of taking our function and reflecting it across the x-axis. Let me show you a very simple example. You might remember the square root function. Square root of x. Now, normally, the square root of x, when I draw the graph, kind of looks like this. And I'll just do it dotted. There's our normal function for square root of x. Now, if I want to reflect the graph across the x-axis, all I got to do is put a negative sign in front of the square root of x. And what that's going to do, essentially, is take all of our y values, and I'll just make a very simple table of values, and put in a couple of pretty important points like 1. Well, normally the square root of 1 is 1, but now it's going to go to negative 1. So these y values are now going to become negative, therefore reflecting them across. So if we go 1 to the right, we used to go up 1, now we're going down 1. Same thing if I put in a 2. Well, the square root of 2 with a negative sign in front of it, which is about 1 and a little bit. So instead of going up, it's now going down. And so our graph is reflected across the x-axis. So that's pretty much the simplicity of doing reflections across the x-axis. Not too bad at all. One thing you have to kind of watch is if your function has more than just one term. Remember, you have to negate the entire function. And I'll show you what I'm talking about. If I made my function a little more complicated, and I won't bother you with a fancy graph here, but suppose my function looked something like this. Say it was root x plus 2. Okay, well, if I want to negate this function, then it would look like this. I would have to not only put a negative in front of the root x, but also in front of this. And the best way maybe to see that is if you took, there's your function, and we've put a negative in front. That will cause the reflection across the x-axis. So that's the only little thing you have to watch for with these reflections across the x-axis. You want to negate the entire function, not just one little part of it. It's the whole function that gets negated. Okay. Now let's look at reflecting across the y-axis. Let's change one little thing there. How do we accomplish that? For example, we have some kind of a function, and we want to flip it across the y-axis. Well, not too bad. What you have to do is this. Inside your function, wherever there's an x, put a negative sign in front of that x. Again, within the function. I'll show you a simple example about that. Why don't we go back to the same one that I just used, square root of x. Well, we know what that looks like. Okay, we got this kind of thing. Okay. Now, how do I get to flip it across the y-axis? Well, I'm claiming all I need to do is that. Put a negative sign in front of the x inside the function. Why does that have the effect that we want? Well, let's look at a couple of simple points. Suppose I tried to put a 1 in. Well, let's see. Positive 1 was here, sent me up to 1. This time I'm going to get a negative 1, and I can't take the square root of it. So this is kind of a doesn't work. Suppose, on the other hand, I plugged in negative 1. Well, I would plug a -1 in here, and I would get -1, producing +1, the square root of which is 1. So over here at -1, where there was no part of a graph before, I'm now supposed to go up to +1. And you can see that's going to happen with all the other negative numbers because they get turned positive, and now I can take the square root of those. So I get this kind of a graph. It's reflecting across the y-axis. That's kind of all there is to reflecting. Whoops. You can see that's not too good. Across the y-axis. Okay. Now we've got that all figured out and written down. Reflecting across the x, reflecting across the y. And then I alluded to something earlier. I said, well, there's other reflections that are important. So let's make a little room for the last of the important reflections. All right, let's do, first of all, a little look at what we call inverse functions. Okay, now the idea behind inverse functions, you might recall from earlier math courses, is that an inverse function is supposed to undo what the original function does. And a way of visualizing that is to look at it through the graphs. Graphically speaking, in the original function, we might have points where x gets beamed to a certain y value. Okay, and those are the points that we graph, and it creates the picture of that function. In the inverse function, we want to kind of undo what the original function has done. So in other words, if we take these y values, plugging them into the inverse function, they're supposed to beam us back to the x values, where we started. Now, this gets a little confusing because we always traditionally think of the x numbers as the ones we put into the function, and the output that we get are the y's. So you just have to bear with this and think, well, this number produces this output here, and if we take this output and make it the input into the inverse function, then it takes us back to where we started. It's all a little bamboozling, but we'll see if we can get a kind of a graphical representation here. The idea now is to look at this and say, hey, I'm kind of spinning around the x's and the y's. They're kind of unraveling themselves, and that has the following effect. Reflecting across a certain special line, y equals x. And that's how we get a nice graphical image of a function and its inverse. So suppose we wanted to get a graphical image of the following. Let's say we had a function that looked something like this. Okay, it comes, say, roaring up like this. And I thought to myself, well, that's a pretty good function. And let's say this was the point 0, 1. And I thought, well, that's very nice. There's f of x. I would like to graph the inverse function. Well, all I have to do is produce the line y equals x, okay, which I'll just do as a little dotted line here. Okay. And what I now want to do is reflect this graph across that dotted line. Now, a way you could visualize this that I think has helped me is I just think of this as a piece of paper that I'm going to fold on the dotted line. And if I took some paint and I smeared it along f of x, and I squished the paper after I folded it, where would the paint be on the other side? That's how I kind of visualize where the reflection is going to be. But another trick that really helps you get some good footholds is you can take any of these points, here we have a 0 and a 1, spin them around, just like we're supposed to up here. So instead of 0, 1, a point on my inverse graph would be 1, 0. So there's that point reflected across. So now if I draw my reflection as best I can, I just sort of visualize this coming across. I guess this would do something like that. And this part here would come down, I guess, like so. So this would be f inverse of x. That's the easy way to get a graphical representation of the inverse and its function. Let me show you an algebraic way to handle that as well, and then we'll also confirm the algebra with a quick graph. So, if I'm going to take an example of a function that looks something like this, f of x equals the square root of x minus 2. And somebody says, well, I want you to find the inverse of that. Okay, well, here's how you have to do it. Remember that f of x is the same thing as y. So step number 1 is to make every y an x and every x a y. So again, I'm coming back to the idea of spinning around the x and the y. They just reverse roles. So in a sense, this is it. This is, hey, there's my inverse function, except usually we write functions as y equals, not x equals. So step 2, clean it up and get it so it's y equals. Sometimes that's easier said than done. In this case, I'm going to square both sides to try and get rid of this square root. So I'm going to have x squared equals y minus 2. And then I'm going to add the 2 over. So I have x squared plus 2 equals y. And if we rewrite it so it sort of looks prettier with y equals, there it is. There's my inverse function. Now, let's look at the graph of these two functions and confirm that they are indeed reflections across the line y equals x. In so doing, I think we'll find another very important observation by looking at the two graphs. I'm going to try and squeeze them side by side down here so that we can make a kind of a nice comparison. Actually, maybe I'll put them on the same grid. Don't really need them side by side. Okay, well, let's do that. The first equation, oh, there we are at the top. Y equals the square root of x minus 2. Well, this is the old square root function, but it's been shifted over to positive 2. So you've got to go 2 to the right. There's our little friend, square root of x. Okay, so just have a little translation of 2 units to the right. So there's f of x. Now, this guy here, y equals x squared plus 2, well, that's a quadratic function. That's a parabola that's been shifted up 2. So we'd go up 2, and a funny observation occurs here. Well, if I was going to draw the entire parabola, there's a kind of a left side and a right side, kind of a U shape. Well, let me draw that, but there's kind of a, well, I've got to fix something on here. So here we go. There it is, and then I go, wait a minute. This hardly looks like this if I reflect it across the line y equals x. And this got an extra side to it. Well, here's the thing you have to observe. If we look at, in the original function, its domain and its range. Let's put those two up there. In the original function, remember that under a square root, you have to have a positive number. So in other words, this guy here, x minus 2, has got to be positive. It's got to be greater than or equal to 0. Now if I just move the 2 over, add 2 to the right, that tells me that my domain has to be x greater than or equal to 2. Well, that's no problem. That's what we see here on the graph. From 2 greater than. No problem for my domain. What about my range of this function? Well, if you see at the graph here, it's going to be y values that are 0 or greater. So I'm just going to write that down here. The y values are greater than or equal to 0. Now, if you run into a situation like this where you're going, I got 2 halves of a parabola and I can't really consider both of them the correct inverse, all you got to do is remember x's and y's reverse roles. So in my inverse function, my domain and my range are going to have reversed roles. In other words, the domain, x greater than or equal to 2, basically tells you how your range should behave. It should be greater than or equal to 2. Now, of course, being it's a range, we're referring to these as y values. So we want our y values to be greater than or equal to 2. Well, that's pretty obvious with our graph. So we're happy with that. But now we look at this, the range it says here, y's are greater than or equal to 0, becomes our domain. Greater than or equal to 0. So our x's are to be greater than or equal to 0, which would mean we only want the right half. So this left half is gonzo. Now, that also matches the idea of reflecting across the line y equals x. It's a very important little observation that domain and range switch their roles down here, which is consistent with what we've been doing the whole time. X and y switching with inverse functions. All right. Well, I've got one last example to look at, just because it can be a little algebraically messier than the previous ones we've seen, and sometimes an algebraic mess has to be looked at, analyzed. Yeah. So, this example looks kind of like this. If this is our function, and we've got 5 over x squared plus 1. Okay, well I'm not even going to try to graph that, but I'm going to try to find its inverse algebraically. So the first thing I would do is go, well, that's a y. So step 1 says I'm going to write an x in that location. And over here, that x squared, I'm going to write as a y squared plus 1. So this is my inverse. Okay, so step 2, we've got to get the y by itself. So I think what I'm going to do is I'm going to multiply both sides by y squared plus 1. So I'm just going to multiply everything by that, just to get rid of the fractions. So on the left side, I'm going to have x times this stuff. And on the right, I'm just going to have 5. Then I'm going to divide by x. So I've got y squared plus 1 equals 5 over x. We can now subtract 1 over to that side. All right, starting to look happy. And we're going to square root both sides to get y by itself. Now here's an important little point. Okay, happily I square root this. Da-da-da. Oh, got to do one thing. When you square root, you have to give the possibility it could be positive or negative. So, that's a very important little point, because now we go, just a minute. This thing won't be a function. When you have plus or minus, what happens is, if you pick a certain x value and you put it into this function, and a y value exists, there's going to be 2 y values. And by definition, it can't be a function if it has 2 or more y values. It's only allowed to have 1 y value to be a function. So this is not a function. We certainly found the inverse, but sadly, it is not a function. So, can't always end every lesson on a happy note. So that's where I'm going to stop there. We've looked at reflecting across the x-axis, the y-axis, and the line y equals x, involved in the whole business of inverses. And I think it's a good time to stop. So, catch you later.